Good morning. Today, we're pulling back the curtain on Shopify's mTLS journey. It's been quite the ride, and we've got some fascinating insights and lessons to share. But first, some quick introductions. I'm Michelle Malley. I've been at Shopify for nearly 5 years and joined InfoSec in 2023. I was a contributor on the mTLS project and continue to work on securing Shopify's infrastructure.
And hey, I'm Dani Santos. I'm a senior InfoSec engineer, and I joined the team in Shopify back in 2020. My recent projects involve increasing the adoption of mTLS for internal service-to-service authentication and using attested identities for ACLs. Here's what we're going to be covering today. We're going to start with a brief refresher on Zero Trust, and then we move on to talk about workload identity and adopting SPIFFE. Then we cover some options for service-to-service authentication. We also talk about how we do certificate management, observability, and we finish with a demo followed by key takeaways. We're going to be showing snippets of the demo throughout the slides, but we will have a final session with a video showing all the pieces together. But first things first, why does Zero Trust matter? Zero Trust is a concept founded by this fine gentleman, John Kindervag. It's been around since 2009, and it centers around the belief that trusting is a vulnerability, and security must be designed with the strategy never trust, always verify. We have seen a growing push for the Zero Trust model across companies and government agencies. The latest technology trends for 2025, published by O'Reilly, states that there was a 13% rise in interest in the topic. Now, let's take a step back and try to understand why this is the case. Oops. You remember in 2020 we had the pandemic, and it triggered an unprecedented shift in how organizations operate. And this global crisis accelerated the consumption of toilet paper and also accelerated the adoption of cloud infrastructure as companies rapidly adapted to support remote work and digital operations. Also, bring your own device policies fundamentally changed how organizations approach security. With scattered workforce across various locations and devices, relying on the traditional perimeter security model, or castle and moat, became problematic, to say the least. In Zero Trust, we always verify the identity of every entity requesting access, both human and non-human. Non-human entities like VMs, containers, applications, and services are called workloads. This verification process can be achieved through various mechanisms, but because mutual TLS or mTLS ensures that both parties at each end of the network connection are what they claim to be, it is one of the primary and recommended mechanisms for service-to-service authentication. This talk is going to focus on how we implement mTLS at Shopify to verify these identities. Okay.
So, what makes up a workload identity? What are some of the challenges organizations such as Shopify face when implementing and managing them? To illustrate how workload identities work, consider how we use passports as identity documents. What makes a passport different from any other piece of paper with your name written on it? Well, they are issued by recognized authorities and include unique identifiers such as physical attributes and a passport number. They also use watermarks and laser perforation to prove authenticity. This same concept applies in the digital world. Instead of passports, we use digital identity documents like X509 certificates to authenticate humans and workloads. Instead of government authorities, we have certificate authorities. Subject names and the serial number serve as unique identifiers, and instead of watermarks and laser perforation, cryptographic signatures are used. Machine identity management is complicated. Let's see why that is. Machine identities greatly outnumber human identities about 45-1, and they can't rely on traditional security like MFA. Also, their creation is often spontaneous and decentralized. They tend to accumulate excessive permissions and outlive their purpose. Finally, a small change in permissions could break critical systems. But machine identities aren't alone in their complexity. Today's infrastructure as a whole presents another set of challenges. Organizations are juggling multiple technology stacks. They're also managing a mix of cloud services and on-prem systems. As these systems grow more interconnected and development accelerates, one thing becomes clear. We need these different systems to work together seamlessly. That is why SPIFFE, Secure Production Identity Framework for Everyone, was created. The CNCF graduated project is an open source framework designed to provide a secure and standardized way to manage identity in cloud-native environments. A URI, which serves as the SPIFFE ID, is crucial for uniquely identifying your workloads in your infrastructure. There are some specific constraints in place. For example, the @ symbol cannot be part of the URI. The meaning behind the path is left open-ended and is the responsibility of the implementer to define. At Shopify, this is how we structure the URI to give us enough metadata. The trust domain is in purple and the subject path is in yellow. This structure captures our workload identity pool, the identity of the Google service account, and the corresponding project, all within the subject alternative name of the certificate. We use common expression language to format the path to our desired structure. Dani, tell us about SPIRE.
Yeah, thanks. So to implement SPIFFE, you can use SPIRE. It's also a CNCF graduated project. It stands for SPIFFE Runtime Environment. You get agents running on every node, managing the full identity lifecycle for you. While SPIRE is the reference implementation, SPIFFE concepts can be implemented through various platforms and services. Google Cloud is one of the officially recognized integrations. At Shopify, we use Google Cloud Certificate Authority Service for our private certificate authorities, and we leverage identity reflection for federated workloads to obtain a SPIFFE ID. This means we don't run SPIRE agents ourselves, but we get all the benefits of standardized identities across our infrastructure. When adopting SPIFFE IDs, though, we did run into some challenges. One notable example has to do with our Kafka infrastructure. By default, Kafka requires the use of the distinguished name for managing access control lists, as you can see in the highlighted documentation. However, when obtaining a certificate from Google CA service using reflected SPIFFE mode, we face a mismatch. Because the distinguished name is mutable and can't be verified, Google ignores it, and all we get back is the send URI with the SPIFFE ID, and this creates a challenge for Kafka authorization, which expects to use the DN for access control decisions. The way we solved it was by building a custom principal builder in Kafka. There are some open source solutions, as you can see here on this GitHub repo and this Kafka improvement proposal, but we have our own implementation. Our custom builder parses the SAN URI containing the SPIFFE ID format and maps these identities to appropriate Kafka ACLs. Speaking of challenges with workload identity, let's explore some broader challenges we faced when implementing mTLS at scale.
At Shopify, we have millions of pods, thousands of nodes, and hundreds of clusters. This scale makes internal service-to-service communication challenging. To address this, we require robust solutions for service discovery, load balancing, and traffic management that ensure performance and resilience across our distributed system. In the industry, there are several established approaches to service-to-service authentication. These include service mesh solutions like Istio, cloud provider solutions like Google's application load balancers, and Kubernetes native approaches with Ingress controllers. Each of these approaches represents different trade-offs between security, complexity, and operational overhead. Let's examine why these trade-offs matter at scale, starting with perhaps the most talked about solution, service mesh. Service mesh technologies like Istio offer an appealing solution for service-to-service authentication. The mesh provides strong workload identity through X059 certificates, automatic certificate rotation, and mTLS between services, all managed through sidecar proxies. On paper, it's a comprehensive security layer that handles the complexity of service authentication for you. But let's talk about some cons. You're adding significant complexity because each pod needs a sidecar container, consuming extra CPU and memory. At our scale of millions of pods, this overhead becomes substantial. There's also the operational burden. You need to manage the mesh itself. It's not just another layer, but a whole new control plane to maintain alongside Kubernetes. While we do use envoy proxies for specific use cases, for example, in Elasticsearch, for the majority of our services, we've opted for a different approach. There are also some cloud provider solutions for service-to-service authentication. Google Cloud, like many other providers, offers internal application load balancers. mTLS can be configured on the target HTTPS proxy resource. With this solution, you are provided custom mTLS headers by default that can be passed to the backend. This solution does have trade-offs. A managed service means there is no need to manage replica sets or worry about node failures. There is seamless integration with other cloud services like IAM or cloud monitoring solutions. And you get built-in security features like DDoS protection. However, vendor lock-in is a con, requiring a massive infrastructure overhaul when changing providers. You are also restricted to features provided by the cloud provider, and costs can quickly escalate with high traffic. Dani, what are some other options?
Yeah. Ingress-NGINX, you might be thinking, Ingress, nightmare. Luckily, we didn't get affected. No public admission webhooks. Anyway, it has been a core component of our infrastructure since 2018, when we adopted Kubernetes. And some teams are currently exploring the Gateway API, but Ingress-NGINX is still a primary tool for service-to-service authentication, internal one. It supports multiple authentication methods, including basic auth, basic map, OAuth, and mTLS. Well, I have a confession to make. We might have some internal services authenticating using basic auth. But we've been on a continuous journey to get rid of basic auth everywhere in favor of mTLS. But let's see why basic auth could be problematic from a security standpoint. Username is our only way to identify clients, and it's not verified. Multiple services often share the same credentials, and there's no automatic key rotation, which means we have long-lived credentials. By the way, the lack of automated rotation isn't just a basic auth problem. Developers often forget to rotate or simply don't spend time doing it because it's working until it's not anymore. Some keys might expire or someone might delete them accidentally. With automatic key rotation, teams don't need to worry. It's way less error prone. Here's a quick story. Once upon a time, there was a Cloudflare key with admin powers in use by a service. It was set to expire after 4 months. The team in charge didn't know it was time to rotate, and it resulted in a partial outage. I'm sure this is a story that you've heard many, many times before. Maybe some admin got an email warning from Cloudflare about the expiry, or they saw it on some dashboard, but the developers maintaining the service had no idea until end users reported problems and came complaining on Slack. So yeah, storing keys with no automatic rotation is a common issue across the industry. Here we have Ben Arendt from Teleport. I saw their booth there. He's vouching for Zero Trust access for GitHub. They mention forever living SSH keys or personal access tokens used to access GitHub repos. Once the SSH key pair is generated, do developers actually often rotate them? Or they do so only when they have to, when they're assigned new laptops? How about personal access tokens? Do they always set them to expire? Anyway, the solution here is also SSL certs, which auto-expire, give us better auditability, etc. Now, back to Ingress-NGINX and our beloved authentication method, mTLS. Here's an example of configuration. You can use specific annotations. They can all be found in the official Ingress-NGINX docs. I'm just going to go over the key ones used for the demo. authTLS secret points to the Kubernetes secret containing the client CA cert. authTLS verified depth sets the verification depth for the certificate chain. For example, you can set it to 2 if you have a root and a subordinate CA, or 1 for self-signed certs. In our demo, we have authTLS verified client set to on, which means that the client cert must be signed by a certificate that is included in the secret key ca.cert. Have authTLS pass certificate to upstream. It passes the entire raw client certificate to the server. This is the only way we can access the SPIFFE URI, which we're using for our ACLs. Unfortunately, Ingress-NGINX does not forward this value alone as a request header. And this is what the content of the header looks like. In our experience, it was a hard sell getting teams parsing this. We get this ugly URL encoded string, notice the %20 for spaces and stuff. Basically, we have to clean the PAM. It would be so much nicer if we could just get a header with the send URI field only, just like what Google offers, as Michelle showed before. But at Shopify, we have something called hack days. We have 3 days to hack on whatever we want and experiment. So we created a project to dynamically extract the subject alternative name, SPIFFE URI, from the client certificates and forward it as a request header. But that involves writing Lua scripts, and no one on our team knows Lua. So we resorted to our friend GPT. This code here takes the PAM cert, converts it to dir format, parses the ASN. It does a bunch of things, but we never opened the PR upstream, as we thought it wouldn't be accepted, and we can't really attest to the code quality. Has a bunch of nested loops, but it works, kinda. There was a lot of back and forth with the bot, meaning there's considerable craft in this diff. Anyway, there's an option to create some helper function, or you can use some library to help with the parsing. For example, in Golang, URL query on escape is your friend. Well, we all agree that mTLS is great, but with mTLS, certificate management grows more complex, right?
Yes. Managing multiple certificate authorities can quickly become challenging. To simplify this at Shopify, we chose to implement a shared private CA for all of our internal service-to-service mTLS communication. This is how we set up our PKI. We went with a 3-tier approach for our certificate hierarchy. First, there's our root CA. We keep this one locked down. It's basically just there to sign our intermediate CA. The intermediate CA does all the heavy lifting. This middle layer gives us an extra buffer of security, so we're not putting all our eggs in one basket. Finally, we've got the leaf certificates that our services actually use day-to-day for mTLS. These are what our services present to each other to prove their identity. Adding that intermediate layer might seem like extra work, but it gives you additional guarantees. If something goes wrong with the intermediate CA, we can revoke and rotate without having to touch our root of trust. Talking about rotation, one of the most difficult aspects of certificate management is rotation. How do we rotate certificate authorities? We begin the certificate rotation process for our shared CA well in advance of expiry to ensure a smooth transition. The rotation process for the root CA begins 1 year before expiry, and for subordinate CAs, it begins 6 months before expiry. At Shopify, we use an alert rule like this to notify when CAs are nearing expiry. To rotate root CAs, we follow these steps. First, create a new root CA. Then add the new root cert from the new CA to the trust stores. Next, create new subordinate CAs. And lastly, delete the old root CA. For rotating subordinate CAs, first we create a new subordinate CA. Then we disable existing subordinate CAs. And finally, we delete the expired subordinate CA. After CA rotation, we test with our certificate management tool locally. We verify it can successfully request and receive certificates from the new CA. So that's for certificate authority management. How about client and server certificates? Here's another CNCF graduated project, a well-established tool for managing certs in Kubernetes, Cert Manager. We use Cert Manager to automate the issuance and renewal of certs for many of our GKE workloads. As a team, we love using it because its open source nature means we don't have to worry about maintenance. Cert Manager seamlessly integrates with multiple cloud providers and services. Initially, we were using HashiCorp's Vault, but then transitioned to using Google Certificate Authority Service. And the transition was easy, thanks to Google CA's Issuer. It serves as an external issuer for Cert Manager that uses Google CA Service to issue certs through managed private CAs.
Yeah, Cert Manager is great when you're talking about Kubernetes environment, but how about non-Kubernetes environment? We have this in-house tool written in Golang, which allows engineers to mint a cert using their own credentials for local development. It's been in use for 4 years now. It's a binary that can be installed with Homebrew, and there have been use cases where this is needed for VMs as well. We also have some resources running in clusters without Cert Manager installed, and for those, the general recommendation is to run the tool as a sidecar container. It's lightweight and provides a flexible method to get certificates. It can be run as a background process or as a one-time job. We also have some serverless applications. More specifically, we use Google Cloud Run. When we talk about containers running on demand, we can't run our tool as a daemon. If the instance doesn't get requests, it shuts down and only reboots when a request is sent. So for this, we use Cloud Run scheduled jobs. The job is set to run several times during the day and takes care of renewal in case of upcoming expiry. And the certificates are stored in Google Secret Manager, exposed to the instances as environment variables. Talking about Secret Manager, this in-house tool offers 4 storage options, catering to different use cases: local file system, Google Cloud Storage Bucket, Google Secret Manager, and Kubernetes Secret. It does require specific IAM permissions for the Google services, and to store it as a Kubernetes secret, it needs specific role binding. Here's an example of the configuration we created for the demo. First, we have a specific service account for the job. We give it create to create the secret initially and get an update for the renewal logic. Given the rise in interest in serverless applications internally, and also noticing a rise in the use of our certificate loading tool, at some point we had a lack of clarity and consistency in our certificate management infrastructure. So it also became kind of hard to maintain both Cert Manager and the tool to do the same thing. And after some research and talking with other teams, we decided on using our custom tool to manage all client certificates. We decided to follow a pattern similar to the one we were using for serverless applications, where jobs handle certificate creation and updates. One critical consideration with this approach is the order of operations. Certificate data must be available before a service container initializes. To address this, we deploy an initial job that runs once to mount the Kubernetes secret, making the TLS cert immediately available for the application at bootstrap time. And then subsequent certificate issuance and updates are handled by the Cronjob running on a scheduled basis. To guarantee that the certificate loader job completes before the deployment is created, we use Carvel KApp. With KApp, we can wait for specific resources types to reach a ready or complete state before proceeding. In our demo, though, we chose to implement Argo CD sync waves, which also effectively manage deployment sequencing. Michelle will demonstrate this later in our demo session. Here we have a demo job deployed to our Service A namespace, similar to the one we have internally. The job runs our binary. When we run it, we call the new store function, and we know we're running a Kubernetes environment by checking if the namespace information is mounted, meaning we're going to store the certificate data as a secret. We create a secret called mTLS certs containing tls.cert, which has the subordinate and leaf certificate bundle, tls.key with the private key, and ca.cert with the shared root CA, which is trusted by both the client and the server. Let's see this in action. We deploy the initial job, and then we wait for the job to finish running. And after it's done, we can see the secret created there. When we describe the secret, we see that it correctly injects the data as expected. And when we decode the client certificate, we see the SPIFFE URI right there. Yeah. Our deployment resource mounts the certs volume and creates files using the secret mTLS cert, which was created by the initial job run. And our client finds the bundle with the subordinate and leaf, as well as the key to make the request to the server. It also uses the ca.cert to validate the server certificate. For subsequent renewals, we use cron jobs, which run every 6 hours, 4 times a day. However, if every service uses the same cron expression, we might run into an issue where we have several containers making thousands of concurrent requests. And then, so we address this by using a customized function to dynamically generate the schedule for each service, randomizing minutes and hours. This is done in a deterministic way so that every time someone renders the configuration, it doesn't generate a brand new schedule for the same service, triggering redeployments of the cron job all the time. So we use the name of the service to create this unique fingerprint by using a salt function. So how often do renewals occur? The cert tool checks the time to live of the certificate, and when a cert reaches 50% of its lifetime, the tool run as a cron job will attempt to renew it. Let's imagine here a certificate that's valid for 10 days. And let's imagine there's a failure of some sort. Say someone accidentally deleted IAM permissions. Since the cron job runs 4 times a day, any error in issuing the certificate will result in 4 alerts per day. For the next 5 days until expiry. That's a total of 20 alerts. This should provide service owners with enough time to take action. So talking about alerts and monitoring, let's take a closer look at our observability stack. There you go.
Another key part of the certificate management lifecycle is collecting metrics to better understand potential failures. Our observability stack uses Grafana, Prometheus, Tempo, and GCP Logs Explorer. Grafana is a web-based platform for visualizing metrics, logs, and traces through customizable dashboards. Prometheus is a time series database that collects and queries metrics, and we get application traces from Tempo and CA logs from GCP's Logs Explorer. This is an example of the types of logs we ingest from GCP. If you're interested in learning more about observability at Shopify, check out this recent talk by Sebastian and Matt.
Cool. Let's go over some metrics. If you're using Cert Manager, you get metrics exposed in the Prometheus formats already from the controller, webhook, and CA injector components. They're available at the standard metrics endpoint on port 9402 of each component pod. Cert Manager exposes metrics such as the date after which the cert expires, the number of seconds within which the certificate should renew. It also exports metrics about the health of the certificate object and sync error count, for example. They allow us to capture failed certificate issuance and renewal problems, being critical for preventing outages related to cert expiry. Our in-house tool emits metrics similar to the way Cert Manager does. However, since this tool focuses on client certificates for mTLS, we don't have Acme-related metrics. Some of the metrics we expose are sync success, sync failure, cert expires in seconds. We use stats-D for these metrics, and we use tags for better error classification. Sync failure uses error type tags to provide more information about issuance or storage-related errors. We mentioned our unorthodox approach, where we have jobs and cron jobs managing certificates. Unlike long-running services where Prometheus can regularly scrape the metrics, jobs are ephemeral by nature. They start, execute their task, and terminate, often before Prometheus has a chance to collect metrics. So, how do we ensure continuous monitoring? One way to get indicators that there's something wrong when issuing the certificates is by observing the job status by using kubestate metrics directly. If you're using Kube Prometheus stack, you get it out of the box. You can see it in action here. The key metric we're looking at is kube job status failed. Why is this useful? It's an early warning system. It won't tell you exactly why the job failed or give you business-specific metrics, but it's an excellent first line of defense. But if you want to reliably capture metrics like issuance failure or request duration, one option is to use Prometheus Push Gateway, which acts as an intermediary. The job actively pushes the metrics before termination, and the Push Gateway exposes them to Prometheus. We chose to instrument our in-house tool with stats-D. With stats-D, we have immediate metric pushing through UDP before the pod terminates. We also deploy stats-D exporters that convert these metrics to Prometheus formats, which are then consumed in our Grafana interface, allowing us to set alerts and dashboards. Well, so as I said before, we've been showing bits of the demo throughout the talk. So far, a series of short films or reels. It's time for a feature-length version where we get to see all the pieces together. But let's take a look at the synopsis first. We have 2 services, Service A and Service B, running in separate namespaces in a local kind cluster. They communicate via Ingress-NGINX controller using mTLS. The controller handles TLS termination for us. The Ingress controller validates the client certificate, and then the request is forwarded to Service B. Service B performs additional identity verification and access control. The cert tool manages the certificates that both services use for their authentication. The process begins with the generation of a key pair by the cert tool, which will be used for the certificate signing request. The cert tool authenticates with Google's IAM Workload Identity Federation. It obtains an ID token, which is exchanged for an access token provided by the security token service. And then with the access token, the cert tool makes a CSR request in reflected SPIFFE mode to get the SPIFFE URI, which acts as a workload identity. Finally, the cert tool stores the certificate data in a Kubernetes secret. And the cert tool is going to be pushing metrics using Prometheus push gateway, giving Prometheus enough time to scrape them. Prometheus rules evaluate the metrics and generate alerts for issues like failed requests. The metrics and alerts are visualized in Grafana. Showtime. Yeah. Cool.
To start the demo, I want to walk through a common problem. I have a directory here with many Kubernetes manifest files that I want to apply at once. A standard apply should do the trick, but as we see, that didn't work. Resources were applied in the wrong order, resulting in errors. Doing another apply will fix this, but it is not an ideal flow. There has to be a better way to conveniently deploy everything with one command in the correct order. Well, the answer to that is Argo. I'm going to begin with ensuring that the Argo UI is up and running, and to do that, I'm just going to simply port forward the Argo service. And we should see that the UI is available. So I'm in the same directory as the previous scenario, but this time I defined an Argo application and added the necessary sync wave annotations to my manifest files. Now all I have to do is apply the Argo application manifest file. Let's go to the UI and see the syncing in action. Awesome, all my Kubernetes resources have successfully deployed in the correct order. I get an amazing overview of all the objects with the built-in UI, and I can easily see the health of everything. And here we have some information about the latest commit from our repo that Argo is choosing to sync from. To better understand how this works, let's take a look at the Argo annotations present on the manifest files. The namespace is configured with a sync wave annotation value of -1. Lower numbers indicate earlier creation, while higher numbers trigger later creation. By setting it to -1, this namespace is prioritized to be created before other resources in the cluster. For the job, we have the sync wave set to 1, meaning that it will be deployed after the namespace. Our deployments first need the job to run to mount the certs, which is why for them, the sync wave is set to the number 2. Similar logic is applied to services and ingresses, where services have to be created before ingresses. Now let's demonstrate how access control lists work with mTLS. On the top left terminal, we have service A, and on the top right terminal, we have service B. First, watch what happens when service A tries to access the /internal/FIPI endpoint. As you can see, service A successfully authenticates using its certificate and gets access to the endpoint. I'm going to zoom in on the SPIFFE ID that identified service A to service B during the mTLS flow. Now let's test our ACL in a different way. When service A tries to access /internal/Z, something different should happen. Even though service A is still using the same valid certificate for authentication, notice the red error message, access denied. This is our ACL in action. Service A is authenticated, but not authorized to access this specific endpoint. Now for our failure scenario. Some users are reporting issues with the application. To find out why, I'm going to head over to Grafana and then go under the alert rules section, and then I'm going to filter the alerts to those that are firing. As I noticed at the bottom an error coming from the cert tool. As I expand, I see that it's an error with certificate issuance. I will further expand and get a lot more information about the rule that is firing. My hunch is that the job that is responsible for issuing certificates to our pods seems to have encountered an issue. Let's go to the terminal to confirm this. I'm going to look at the status of the job, and it looks like it never completed. We should dive deeper and take a look at the logs from the pod of the job. And there we go. We found an error message. The service account didn't have the correct permissions, which caused the alert rule to fire. And this marks the end of our demo. So, what are the big ideas you should walk away with? Zero trust adoption continues to accelerate, making mTLS not just important, but essential for secure service-to-service communication. When it comes to workload identity, SPIFFE stands out as the industry standard solution, offering a robust framework for service identification and authentication. Remember that authentication isn't one size fits all. Your solution must scale with your organization and address your unique security requirements. For certificate management, you have options. While proven open source tools exist, don't rule out building a custom solution if your needs demand it. CA rotations deserve special attention. They require thorough planning and precise execution. Finally, comprehensive monitoring and alerting are critical. You need to catch certificate issues early before they impact your services and users. Thank you for taking the time to attend our talk. These QR codes link to our socials where you can connect with us. I'll stay on this slide for a moment.